Hello everybody, welcome to Numbers Online School. Today we'll be going through another problem from the East African Mathematical Olympiad 2025. Here's a view of this problem. The real numbers a, b, and c satisfies the inequalities that the absolute value of a is at least the absolute value of a plus b, absolute value of b is at least the value of absolute value of a plus c, and the absolute value of c is at least the absolute value of the sum of a and b. Prove that the sum ab plus c has to be equal to 0. So in this case, we have these real numbers. They could be positive, negative, or 0, but they satisfy this strange sequence of inequalities, and we have to prove that their sum has to be equal to 0. And as you can see, if this equation is true, then for example, b plus c will be equal to negative a, and so the magnitude of negative a will necessarily be equal to the magnitude of a itself, and for the other cases, c plus a will be equal to negative b, which the equation will be true, and a plus b will be equal to negative c, and so the inequality will actually be equality. So if this equation is true, then that sequence of inequalities is also true because they are actually equalities. So we want to prove this for that this is always true, that whenever this equation is true, then this equation, these inequalities are true, then this equation is also true. So how do we do this? In order to do this problem, we have to square these inequalities. Okay, we have to square this both sides of each of the three inequalities. So in this case, we can square the left hand side of the first inequality and the right hand side of the first inequality, in which case we will get that a squared has to be at least b plus c squared. And this is true because the magnitude of a is at least the magnitude of b. And similarly, when you square both sides of the second inequality, we get that b squared is at least c plus a squared. And lastly, also we get that c squared is at least a plus b squared. That. And at this point, you can add up the inequalities to get that a squared plus b squared plus c squared has to be at least the sum of the right hand sides of the three inequalities, which is a plus b squared plus b plus c squared plus c plus a squared. Now we can expand this equation, this expression, and then the expression will be equal to, I'll save you the trouble, it will be equal to a squared plus b squared plus c squared plus ab plus bc plus ca. So when you square out this expression, what you end up with is twice the sum of all these expressions: a squared, b squared, c squared, ab, bc, and ca all together. Now we can separate this, we can make it more clear. We can write this expression as the sum of a squared, b squared, and c squared, plus we can separate this, the other part, as a squared plus b squared plus c squared plus twice ab plus twice bc plus twice ca. In which case, we know that this expression has to be equal to a square of some number. So we know that this expression is a plus b plus c all together squared. Now, because we know that a, b, and c are real numbers, so the sum will be a real number, and the square of any real number is always non-negative. So in this case, this expression is always at least equal to the sum here. It's always at least equal to a squared plus b squared plus c squared. This is because the square of any real number is always non-negative. So this squared is always at least equal to 0. And actually, the equality occurs if and only if this expression is equal to 0. Now, if we take a look back at the string of these inequalities, we started with this sum of the squares of a, b, and c, and then we ended at the sum of the squares of a, b, and c. And so for this to be true, this implies that all these inequalities have to be equalities indeed. So this expression has to be equal to this one, because otherwise If this is greater than 0, this implies that this whole sum has to be greater than this, contradicting this string of inequalities. So what we end up with, we are forced to conclude that the sum of A, B, and C squared has to be equal to 0. Now, a square of a real number is 0 if and only if that real number itself is equal to 0. So in this case, we end up to the conclusion that the sum of A, B, and C has to be equal to 0. And that is the solution for this problem. Thank you for watching.